We are the paradoxical ape. Bipedal, naked, large-brained, long the master of fire, tools, and language, but still trying to understand ourselves. Aware that death is inevitable, yet filled with optimism. We grow up slowly. We hand down knowledge. We empathize and deceive. We shape the future from our shared understanding of the past. CARTA brings together experts from diverse disciplines to exchange insights on who we are and how we got here. An exploration made possible by the generosity of humans like you.
We will be talking about the role that control theory can play to study some of the phenomena that we see in language. In particular, I will be focusing on the feedback relationship that exists between the auditory and articulatory systems in phoneme perception and production. And let me start by explaining what feedback is. So imagine that somebody's singing and that they're giving a pitch that they have to imitate. So unless they have perfect pitch, the sound that they produce is going to have a slight deviation. And if they couldn't hear themselves, the deviation would persist over time. However, most people can hear themselves, so they can correct. And they might overcorrect at first, but because they can hear themselves, they try again and again and again until they match their pitch. And this gives us an intuition for the idea behind feedback. Because we can sense the effect that our actions have on the environment, we can correct and adjust for them appropriately. Now, let me be a little bit more specific about what the feedback looks like in the brain. When the singer hears himself, the information is conveyed to the sensory part of the brain, which sends a signal to the motor part of the brain, which produces the articulation of the mouth, which produces another sound that it's again sensed. And we can write this in a block diagram form, so the signal gets sensed, then it gets processed in the sensory part of the brain. This sends the signal to the motor part of the brain, and it's articulated by the motor system, and which generates, again, a signal that it's later perceived. So is this also what happens in language? Well, let's use a similar intuition for speech. If a person hears a phoneme in their native language, or even a full word, they can repeat it without trial and error. And of course, they can also hear themselves, but there's still a big difference. If we illustrate this in speed-accuracy trade-off space, speech is much more accurate and faster than singing. And this is just an intuition, but let's explore some scientific evidence that we have for phonetic perception and production. So in this experiment, speakers were asked to pronounce a word, but they would hear their own signal distorted through some headphones. So for instance, they were asked to pronounce the word head, but they would hear themselves pronounce the word hid. So let's use some common representations of phonemes to illustrate this better. The axes here correspond to the formants, and this gives us an idea of the distance between the phonemes. So the subjects were asked to pronounce the phonemes in gray, but they would hear themselves pronounce the phonemes in green. And if the speakers were only relying on auditory feedback, one would think that the subjects would want to reject this disturbance by fully compensating and pronouncing something like had. But instead, what the subjects do is they try to compensate for the disturbance only up to a point. So they would slightly modify the pronunciation of head, but it would still never sound like had. And for large disturbances, the amount of compensation from some of the subjects would plateau. And results from this experiment look like this, where in the x-axis we have the amount of disturbance measured in hertz, and in the y-axis we have the corresponding amount of correction from the subject, also in hertz. At a certain point, it plateaus, and the point at which this happens depends on the adjacent words. So because had is a word, subjects plateau at smaller disturbances than if had were not a word. This is what the plot would have looked like if the subjects were fully rejecting for the disturbance. So this suggests that there is an internal feedback between the sensory and motor part of the brain. So there's also many other experimental studies supporting this view. There's similar ones studying the effects of delay instead of signal corruption. There's the famous McGurk effect, where it was shown that subjects rely on motor information to identify phonemes, or recent experiments showing that the motor part of the brain is activated when exposed to speech stimuli, but not for non-speech stimuli. So if we go back to the feedback model that we were analyzing before, we can see that the direction that we have been exploring does not capture the full dynamics. In fact, we believe that there is an internal feedback between the motor part of the brain and the sensory part of the brain. And to study whether this was true, we designed a system with the structures shown in the block diagram, and we tried to replicate the headphone experiments. So we introduced some disturbance in the auditory signal, and we measured the resulting compensation in the articulatory signal. And here are the results from the simulations, where we show the shift in the x-axis and the mean compensation in the y-axis. The orange line corresponds to the response from a system with no internal feedback, while the blue line is what happens when we have internal feedback. The internal feedback results in a much smaller slope, and it also allows to put in saturation as this breakpoint. And the breakpoint in this model is chosen as a parameter since it depends on the word. So even though we're using a scalar system, we're able to capture the same patterns. And here for comparison, I'm showing the experimental results that we just discussed. So I want to show that this model is consistent with other models in the literature. So for instance, in this work, the authors explore the role of the somatosensory cortex in speech production. What I want to highlight here is that the blocks in this diagram correspond to our model, although this model is much more complex. So the green block corresponds to the articulatory system. In pink, we have two sensory systems, so somatosensory and auditory, and then just one motor part as in our model. And if we look at the flow of information, we have this feed forward going from the sensory system onto the motor system, but they also have this internal feedback going from the motor to the sensory system. And as we show in our model, this internal feedback is key to explaining the behaviors that we observe. And this other model for internal feedback has also been proposed for other sensorimotor tasks that are not related to speech. So for instance, in this work, it was about proprioception. And they proposed that the sensory part of the brain and the motor parts of the brain are related in both directions. And in particular, the signal produced by the control part is called efference, and a copy of the efference, so the efference copy, is sent to the sensory part. This is exactly what we call internal feedback, but the advantage of studying these interconnections with control theory is not only to understand these internal structures, but also to mathematically characterize how they're beneficial, for instance, for delay, which is very prevalent in the brain. And in fact, there's already been some attempts to use control theory to understand the structures. Some colleagues in our group have investigated the role of internal feedback in the visual system. In this figure, they show the cortical and subcortical regions and the communication between them. And I highlight here the sensory part in pink and the motor part in green. And in this model, we have the black arrows in the feed-forward direction, but also the blue arrows, which represent the internal feedback. And studying these feedback interconnections with control theory, which is what this diagram looks like, they were able to show that the role of internal feedbacks is to compensate for internal delays. We have reasons to believe that we could get similar results for speech, since there are already theories for neural reuse that speech engages in the same parts of the brain as motor control. So in order to link this feedback structure with the architecture of language, I want to look at what happens during development of the speech capacity. So babies, before they learn how to speak, they babble. And there's been reports that deaf children start the first phase of babbling but do not progress any further and eventually stop because they cannot hear themselves. And this suggests this relationship between the sensory part of the brain and the motor part of the brain. But there's also been studies in babies, and we know that when they are born, they can distinguish almost any phoneme. But as they start babbling and their articulation converges to their native language, their ability to distinguish phonemes diminishes. So it looks something like this. When babies are born, they can distinguish all this variety of phonemes, and as they start articulating, they start clustering a lot of sounds into the same phoneme. So this shows the importance of this internal feedback between the motor part of the brain and the sensory part of the brain. And this is just an animation, but here is a real plot of experiments where people have to listen to sounds and label them as specific phonemes. Something that's striking is that the great amount of consensus among participants, despite the frequencies of these sounds being very close to each other. So some people even suggest that we have mental representations for phonemes and that those are not just informed by the phoneme frequency, but also by the articulation needed to produce a given sound. And just as an aside, babbling has been reported in many other species that show complex articulation, so it would be very interesting to study the role of feedback there as well. And we can now study the role that this feedback plays in the speed and accuracy trade-off that I mentioned at the beginning. So if we kept the ability to distinguish phonemes as well as babies do, we would be very accurate, but also very slow, because every time we hear a sound, we would have a lot of possibilities to match it to. On the other hand, one could think that working with all of these clusters would make us faster but inaccurate, because there are a lot of different sounds that we map together. However, we're never faced with the task of having to recognize an individual phoneme, and instead we rely on words. So because the set of phoneme strings that constitute words is much smaller than the set of all possible phoneme strings, that makes us both fast but also accurate, because we rely on our knowledge of the lexicon. And we call this constraints that deconstrain, because by constraining the strings of phonemes that are possible, we're deconstraining the space of what is possible in terms of speed and accuracy. But something we can ask is, where do these constraints come from? Why does the lexicon look the way it does, and why some phoneme strings are allowed but not others? So the standard answer that phoneticians give to this question is co-articulation. Although this does not fully constrain the lexicon, it does rule out many phoneme combinations and strings because they would be too challenging to articulate. Here is where the motor feedback in speech perception plays a role, because since we are aware of our own motor limitations, we have intuition as to how to shape words with the phonemes of our language. So our own cognitive constraints are generating the constraints that build the architecture for language, and that, as we've seen, deconstrains the speed and accuracy space. And similar ideas applies in the broader context of language architecture. Here we're borrowing the name and some of the ideas postulated by Ray Jackendoff and hint at how these ideas of constraints that deconstrain can apply more broadly in language. And in fact, by constraining the set of phonemes, we have words that make us faster and more accurate in the perception system. And while phonemes are only equipped with phonology, words have both phonology and semantics. And we can continue to go up this architecture, and by introducing sentences with minimal syntax, we are constraining the way in which we can put words together, but this gives us further possibilities for communication. And lastly, we can add paragraphs too. So these structures are very similar to the ones that we study in control theory. We call these elements levels, and we call these functional aspects layers. And by constraining the structure of this architecture, we're effectively deconstraining the possibilities for speed, accuracy, but also evolvability, learnability of the system, which in this case is language. And in particular, a key feature of these architectures is their ability to evolve by adding layers and levels, which is precisely what the proposals for language evolution based on the parallel architecture suggests. So these constraints are often derived from what we call laws, which in the case of language correspond to the constraints in the hardware of the brain and the articulatory system. And this all happens through what we call stages, which are basically processes, and I explained a very simple one today, but we believe that control theory can offer a set of tools that can be very valuable to study language.
So, Carmen, thanks for that great setup, and I'm just going to have a few remarks about the broader context here. So what we want to do, as Carmen pointed out, was try to start explaining how the brain implements this parallel architecture of language. And so what we claim is this is also a parallel architecture. So the brain also uses a parallel architecture, has levels, layers, stages, and laws. And I'm going to very quickly go through this. So our starting point is a pretty conventional view of the levels and layers in the brain, and that came from Terry. And we have now this paper which tries to do this in sensorimotor control, and we call this a layered architecture. Now, actually, we might prefer to call it a parallel architecture. I think that's actually a better word. It includes layering as part of it. And in this case, it's for biking. So imagine we're biking down a twisting, bumpy trail. We want to really simplify this as much as possible. We can't actually do this experimentally. So we have a virtual version, which has trails and bumps in a virtual game. And so what that lets us do is explore experimental settings that would be either deadly or impossible in the real world. But that really lets us push the theory versus the experiment in ways we couldn't in the real world. So what you'd like to do is have a system that was fast and accurate. And humans, in fact, do this with speed and accuracy that is quite remarkable. And in the video game, they learn it very quickly. The problem is, if you just naively look at the hardware, this seems completely infeasible because there isn't any fast, accurate hardware that you can build out of spiking neurons. So how is this done? We claim the way it's done is the way it's done in a lot of technology and in the cell, which is you have layers that specialize in trails and bumps and work together. And this is what we call a diversity-enabled sweet spot. That is, you have diversity in the components, and if you combine them with the right architecture, and only with the right architecture, do they give you a diversity-enabled sweet spot, which is fast and accurate, even though the parts are not fast and accurate on their own. So that's why there are layers, and that's true throughout technology and throughout biology, is to create these diversity-enabled sweet spots. And what about levels? Well, the obvious is how would you build this out of spiking neurons? And so what we want to do is look at spiking neurons, but again, they have also laws that constrain what's possible. And so again, you can have accurate nerves and fast nerves, but there is no nerve that you can build efficiently and maintain that is both fast and accurate. So what happens is you build the accurate layer out of an accurate part, fast layer out of the fast part, and so this creates this diversity-enabled sweet spot in the higher layer, despite the severe constraints on the lower layer, on the lower level. And now we have a theory that models the details of the limits on speed and accuracy in the neurons and nerves, and then says, given that constraint, what would be the optimal control system to build to do the biking game? And so what you end up with is exactly this layered architecture as optimal. And then the algorithms that are in those layers match the behavior of humans extremely well across a huge variety of conditions. We have lots of case studies based on this approach that go back a while, mostly in math and engineering, but some in biology. And here is a list with the journals that they were published in. And if you're interested in any of these and you can't track them down, let me know and I can help. And this is largely viewed as sort of ridiculous that you could have a framework that would deal with all these, again, not in engineering, but certainly in biology. And there's a lot of confusion about this. And these are very special cases, but we claim they highlight universals. And that, of course, the reaction is that's ridiculous. There are no layers or laws that are new to biology that don't come directly from physics. And so that's a current point of contention. So it's really easy to confuse these results too. So let's just take biking and not language, but you might see the parallels. Biking is easy to learn. And so particularly the game is really easy to learn, but there's no biking organ. So whatever the capability is, it did evolve recently and rapidly. That is, biking, not people, evolved recently and rapidly in the last few hundred years, but it explodes over to hardware, which is in some ways uniquely human. There's nothing like emergence here that makes any sense. And there's no special trails or bumps layers, actually. You're just building on top of tracking and reflex. Now, all of this is enabled by parallel architectures, including languages, but also including the brain. And it's a very confused subject, I think, all across science. And I think users of technology are confused by this. And I think engineers don't make that any easier. This is the paper that I encourage you to read if you want to see what I think is our best example on the sensorimotor side. And then if you really wanted to do this right, you would confuse everybody, but you would say that there's not a trails and bumps hardware. Trails and bumps are learned applications that run on the track reflex hardware, which is implemented in the nerves. So this is obviously a much busier picture, but this would be a little more complete picture of what's going on. And of course, you can keep going. And as Terry has shown, those nerves go all the way down to molecules. So you can track this down many layers, many levels. And we claim it's all running the same parallel architecture. So I apologize for the whirlwind tour, but really thanks for giving us this opportunity to talk about this. And we're eager to discuss this and work with others that are interested in this area. Thank you.